We have talked about several topics in mathematics, the different kinds of functions, factorization, the number system, inequalities, interval notation. Is this curve a function? Is it not? Is this function, does it have a even symmetry? Does it have an odd symmetry? By now, you should be good with these minor topics. But more than anything, we talked about domain. So, knowing the domain, which is a set of all possible input values of a given function, now we want to look at the range. How do we actually find the range of a function? How to find the range of a function. So I want us to look into this topic very closely, take some examples, because that's one of the things that are very important when analyzing a function. So the first one that we'll look at is finding the range of the function f by finding the domain of its inverse. Right. So basically, first we're actually going to find the inverse of a given function. So these are the steps. First, find the inverse of the function f of x. So that's step number one. Find the inverse. We usually denote the inverse by f minus of x of the function f of x. How do you do that? There's the steps are also very simple here, because the first thing that you do, you just interchange x and y, and then secondly, after you have done that, make y the subject of the formula. Right. So that's the first thing. You find the inverse, and then once you have found the inverse, that's the second thing that you need to do. Find the domain of the inverse. Find the domain of the inverse. That's what you do. Once you find the domain will be some d of f inverse, which is going to be x is an element of real numbers such that blah 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 x blah blah blah, something of this kind. And then the next step that you will do, you will just replace d inverse with r of the original function and replace x with y. Then you will find the range of the original function. Right, that's what you need to do. So here, once you replace this part here, you will end up having r of f is equal to replacing x, y is an element of x such that blah 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 y happens. Right. So basically this principle is like this. Every time you're interchanging x and y, you are actually interchanging the asymptotes. You are actually interchanging the domain and the range. Hence, we are saying that if I'm good with the domain and I can find the domain of the inverse, the domain of the inverse will actually be the range of the original function. If I am good with finding the range of the original function, then that range will become the domain of the inverse function. That's all there is to this thing here. So let us take some examples here. So the first example will be find the range of f of x is equal to x minus 1 all over x plus 1. Right. For the domain, this is actually pretty easy because this is only going to be undefined when the denominator is equal to 0 or when x is equal to minus 1. So that's when we will actually end up having a domain. But we have no idea how to find the range of this particular function, especially if we don't know how to plot it. So this method here is actually avoiding plotting anything. We're just gonna try and find the inverse of that. So first step, we interchange x and y. In other words, you first rewrite this as y is equal to x minus 1 divided by x plus 1. And then you interchange it. Where there is y, I'm going to place an x, and where there is x, I'm going to place a y. So we're going to have y minus 1 divided by x, divided by y plus a 1. And then the second thing here, I'm going to cross multiply. I will have x and y plus 1 is equal to y minus 1 times a 1, which is just the same thing here. And then I'm going to distribute here. I'm going to end up having xy plus x is equal to y minus 1. I'm going to take everything this side to the left, and I will end up having xy plus x minus y plus 1 plus x. No, this is not x. So this x is this one minus this y, because it's jumping the equal sign, is changing the sign, jumping the equal sign, is changing the sign, is equal to 0. Now, I want to make y the subject of the formula. Anything that is not going to help me with that, I move it to the right hand side. Now I end up being left with xy minus y is equal to minus x minus 1. This is going to change the sign when it's jumping the equal sign, and this one is going to change the sign when it's jumping the equal sign. And then I factorize here because the common factor is y, and then I have x minus 1 is equal to minus x minus 1. And then I have my y is equal to minus x minus 1 all over x minus 1. Now, if you look into this function here, this function here is the inverse of x, which is minus x minus 1 all over x minus a 1. Now, the question you should be asking yourself when you're trying to find the domain of f is simple as this is going to be the domain, that is x is a set of all real numbers such that. Now, let's look into this. What are the values of x that will make this function undefined? I can take the negative values and plug here in the numerator. There is no undefined there. The only time this will be undefined is when this denominator is equal to 0, and that is only going to happen if this x here is equal to positive 1. That's the only case that this will happen. So if I have x is equal to 1, this will be a 0. But now, the domain is the set of all input values that make the function defined. This value here is the only value that is making this function undefined. Therefore, I don't want that to happen. So as long as x is not equal to that, then I have my actually domain of this inverse. Now, if I replace this and say, I want this to be RF, I mean the range of the original function, x is y is an element of real numbers such that y is not equal to 1. This one here is the range of the original function. Range of the original function. Right, so this is the correct answer that we were looking for. Let's actually look at another example again. And this example, I'm going to call it number 2. And then number 2 is saying that find the range of the function. Of course, it is a function first. of the function f of x is equal to natural log of x squared minus a 1. So I have this function here. Whenever you're seeing this lane or natural log, you must know that it is the same as log e of x squared minus a 1. So log base e is the same as a natural log. So that's what is important. What is the solution? First of all, I just want to rewrite f of x is equal to log e of x squared minus 1. And then the first step is always gonna be interchange x and y. Where there is y, I'm gonna place an x. I keep the log e, and then I have my y squared minus a 1. So that's what we're actually doing. Now, this one here is the inverse, but I don't want to write it in a logarithmic form. I want to write it in an exponential form so that I can make this y the subject of the formula. If you remember last time, we said that whenever I have a number equal to the base raised to an exponent, this is always equivalent to saying I have an exponent which is equal to log. I have the base here is down here, and then I have a number inside. So if you look into this equation here, you will find out that the number is inside. I want it out, so I will end up having y squared minus 1 is equal to the base. The base was e, so we will end up having e raised to an exponent x. So this was an exponent. Now y squared is going to be equal to e to the power x plus a 1. Right. Now that we have that one to solve for y, then I'm gonna take the square root on both sides, and then I'll end up having e to the exponent x plus a 1, and then I take the root on both sides. Now, if you take a look into this, you will find out that I just took the root. There is no plus or minus here. I have taken the root here. Now that we know that this number here is bigger than 1, and this one is this is going to be bigger than 0 plus that is bigger than 0. So the root here is always gonna be defined. But suppose we did not know that. All we know is that the square root should always be a positive number. This side, I'm gonna keep the root as it is. I don't want to change it because I don't know what that number is. But if you look at this point here, you will find out that this is the same as just the absolute value of y, which is equal to plus or minus y. So this is going to be equal to the square root e to the power x plus a 1. Now, this plus or minus y, I can always just move it to that side or divide by whatever that constant is, and now I'm left with y as it is. So I will have a plus or minus that side, which is e to the power x plus a 1. Now, yes, I understand that this is not a function because whenever I'm plugging a value x here, I always get two outputs. Once you have one element x that is mapped to two outputs, whatever that rule is not a function. It's not a function, but I don't give a damn about whether it is a function or not. What I care about is when will this be defined or some sort of a domain. In other words, my inverse here, if I were to split it into two, let's say I split it to be plus square root of e to the power x plus 1, or I say that if this is plus 1, if y is greater than or equal to 0, and then I say the inverse is equal to minus 1 times the square root of e to the power x plus 1. If I supposed to split that, and given that I know whenever y is less than or equal less than 0, I get that this will be a function and this will be a function. But I don't really care about these two. What I care about is when will this be defined, this square root will be defined, or the domain of this if it was a function, Or to looking at an alternative of this, I would say, if this I'm only considering this, what will be the domain of this? If I'm only considering this part here, the minus, what will be the domain of this? And of course, this is not that very straightforward, because for the square root to be defined, I want e of x plus 1 to be bigger than or equal to a 0. For both this one and that one, this is what I want. But if you look carefully into this, you will find out that by just plotting this, we plot it just like this. This is bigger than 1. An exponential function with the base bigger than 1, it always go this way. So this is y is equal to e to the power x, because this is bigger than a1. So when you have this exponential function, knowing this value is 1, you know that this curve here, this is x, this is y. This curve here, as long as you start after 0, is above 1, and as long as you are below 0, is always below 1. Now, the question is it possible for this function to be negative? Because this is an exponential function that will never touch the axis. Of course, this one is always going to be bigger than a 0. Or you can look it in this way, that the range of this function, the range of e to the power x, is just y is greater than 0, because this curve will never touch the x-axis. So if you look into that scenario, this will always be bigger than 0. A number that is bigger than 0 plus a 1, you always gonna get a number that is bigger than or equal to 0. So this thing that is inside is always gonna be positive for all real numbers. So the domain of the inverse is going to, x is an element of real numbers, and hence we say the range of the original function is y is an element of real numbers. That's it for this number 2. If you still don't get it, we can try another example here and say that this is the third example, but now I want us to look at f of x is equal to ln of x squared plus a 1. Of course, the procedure is very simple here. This one is the same as y is equal to ln of x squared plus a 1. And you know ln is the same as log base e x squared plus 1. Now if you look into this, I have y is equal to log e, and then you have x squared plus a 1. Now, in order for us to find an inverse, I interchange x and y. So wherever I see a y, I place an x, and whenever I see an x, I place a y. That's what I do to get up to here. Now, I wanted to make this y the subject of the formula, but y is inside the log. For us to make this outside, I need to change the logarithmic form and rewrite it in an exponential form. So here, I will end up saying the number y squared plus 1 should be equal to the base, which is e raised to x. And if I were to take y squared, I should be able to get e to the power x minus a 1. And of course, if I take the root on both sides, I have this, I take the root, and this side I have e to the power x minus 1, and then I take the root on both sides. And then if I analyze this a little bit, as long as it is defined, I know that I will always gonna get a positive square root. But if you look carefully into that, this is just the same as just y, which is the same as plus or minus y, which is equal to the square root of e to the power x minus a 1. And then secondly, if you look carefully on this side, you will find out that you will end up having y is equal to plus or minus the square root of e to the power x minus a 1. Now, when is this gonna be defined, the square root? Remember that this is just meaning that you have the inverse of x is supposed to be equal to plus or minus the square root e to the power x minus a 1. Now, we have this inverse here. When will the right hand side be defined? Right. The right hand side will be defined if the inverse, if what is inside the square root is bigger than or equal to 0. So if I have e to the power x minus 1 is bigger or equal to 0, this would be defined. And then, of course, the question is, how do you end up solving an inequality? The first rule is very simple. You change the inequality sign to equality. So you have e to the power x minus 1 is equal to 0. And then secondly, after you found this, you want to find out what are the critical values that are actually making this function equal to 0. And then those values of x, critical values, the values of x that are making this equal to 0. And then I want us to find those values. Secondly, other set of critical values are the set of all values that are making this equation undefined. So if I plug in negative values here, this is always going to be defined. If I plug in positive values, this is always going to be defined. An exponential function is defined everywhere. So we don't have values of x that will make this undefined. I am just looking for x that will make this thing equal to a 0. In other words, I'm looking for e of x such that it is equal to 1. So I am looking for the y-intercept that will make this equal to a1. And if you are looking for this is in an exponential form. And I'm solving for x here, so I will end up having x is equal to log base e and then 1. So I wanted to find the value of log. That is actually the value, the log base e of 1 will give me the value of x. There are two ways to look into this. If you analyze carefully a logarithmic function, remember that whenever you have a function going like this, whereby this is e to the power x, when you place a mirror which along the line y is equal to x here, this position here will be this position. All the exponential functions passes through 1. Now this one in the mirror, it will become a 1 here, and the mirror that is passing through here, I mean the asymptote that is here, it will actually be here if you look into this mirror here. So now that you have this, if you stand at this side, this point will become that point. And if you stand at this side, this actually horizontal asymptote will become this vertical asymptote. And of course, if this curve is not touching this horizontal asymptote, it's not going to touch this vertical asymptote. And this function will go like this. And we know that this one is log e of x. And if you look carefully here, when x is equal to 1, y is equal to 0, which means that log of 1 is 0. So log of 1 is 0. So here we have x is equal to 0 as a critical point. Or you can just punch in the calculator here and just say, I am looking for log e of 1, and then it's going to tell you that it is a 0. And then now you have one critical value. The second step is you always gonna have to draw a number line, and then you place your critical values there, which is 0. And then this is saying greater or equal to 0, which means 0 must be shaded there. And then now you pick a point that is above 0. I usually pick a 1. And then what I do, I take this point and then I plug it there. And then I plug it here, and then I see if I'm getting a positive value or a negative value. So if I take, let's say e, and then I raise this e to a 1, and then I subtract a 1, what will I get? Will I get a positive or a negative value? What we can actually look at here, e to the power x. If I'm picking a value that is above 0, x is this side, the value of the function will always be above 1. So this is going to be positive, or you can check here that you're getting a positive value. So here I will get a positive answer. And if I'm picking a value that is less than 0, I can pick a -1. If I'm plugging in a -1 here, I will end up having 1 over e, right? And 1 over e is less than 1, so we'll end up having a negative there. And this is saying we should look for positive values, so we're looking for that particular region there. So the domain of the inverse is going to be x is an element of real numbers such that x is greater than or equal to a 0. And now, if let's say you go further to find the range, you replace this with r of f, and then after that x with y. So you will have y is an element of real numbers such that y is greater than or equal to 0. So that's how you end up solving our problem number 3. Now, let's look at 2 more problems, and then we can talk about a different method of finding the range of a function without actually drawing it. Let's look at example number 4. Suppose I'm saying that I'm giving you y is equal to e to the power x, and then you divide this by 1 plus 2e to the power x, and I want you to find the range of this function here. Rule number 1 is I interchange x and y, so wherever I see a y I place an x, and wherever I see an x I place in a y. So you end up having 1 plus 2e to the exponent y. And then after that, of course, whenever you have nothing, you can divide by 1, you cross multiply, you will end up having x1 plus 2e to the power y, which is equal to e to the power y times 1, which is the same thing. And then I distribute this side, I will end up having x plus 2 times x e to the power y, which is equal to e to the power y. Now that we have this, you can see this doesn't have any y in it, and this one here having y, this one having y. I want to take this to the other side, and then this one to one side, so that I can factor out these things that have a y. So I will first say I have x plus 2x e to the power y minus e to the power y is equal to 0. This is jumping the equal sign, so it's going to change the sign. And then I take this x to the other side. It was positive this side. Jumping the equal sign will give it a negative sign. And then that side will be minus x. And then between this one and this one, I have a common factor there. I will have e to the power y, and then I have 2x minus a 1. So that's how I end up factorizing that piece over there. And then e to the power y can be isolated if I divide both sides by this chunk here. So we'll end up having minus x divided by 2x minus a 1. So you have this nice thing here whereby you have an exponent which is y. I want to bring it down, and then it should be equal to, because I'm changing this exponential form to a logarithmic form, this e was a base, and then inside I have minus x divided by 2x minus a 1. Now, I have this nice function, and this function is the one that I call it the inverse of the original function, which is log base e minus x divided by 2x minus a 1. So I have this nice function. The question that I have, what is the domain of this function here? If you go back to what we were doing here, we said that a logarithmic function, a very basic logarithmic function, is always looking of this type. So you have a logarithmic function, it's always gonna look like this if this base here is bigger than 1. But if this base is not bigger than 1, it's less than 1, it's always gonna look like this. So it's gonna pass through this point, which is 1 here, but it's not gonna touch it. Now, the domain of this function, which is just log e of x, this is only defined if I were to pick a negative value here and I plug it in the value of x, I will get an undefined, because a logarithmic function is not defined for these negative values. And if I were to pick 0, 0 is an asymptote, so I cannot plug it there. It's always going to be undefined. So the domain of this basic function is always saying x must be greater than a 0. What that's supposed to mean for us? It means that for this inverse function to be defined, whatever is inside here, which is minus x divided by 2x minus 1, must be greater than a 0. So how do we end up solving this inequality? The first step is very simple. You change the inequality sign to equality. So this is supposed to be 0. And then the second thing is you want to find the critical values. So how do we find the critical values? First, we want to find the values of x making the equation equal 0. So we want to find the values of x making that equation equal to 0. This is only going to happen when the numerator is equal to 0. Numerator is equal to 0. That's what is important. So the numerator will be equal to 0 if minus x is equal to 0, which actually means if x is equal to 0. So this is one critical value. Another set of critical values is the values of x making the equation undefined. Now, for this equation to be undefined, it will only happen if the denominator is equal to 0, because that's a fraction. So when the denominator is equal to 0, that function will be undefined. Or when we have 2x minus 1 is equal to 0, or when we have 2x is equal to 1, or when we have x is equal to 1 over 2. So that's also another critical value. Once you have the critical values, it's very easy, because the next thing that you need to do, you want to draw the number line. So this one is 1 over 2, this one is 0, you have a hole, you have a hole. This one, we got it by making the equation undefined, so we always don't shade this one here. But this one is the one that actually has a chance. If here we had, if here we had greater or equal, this one was going to be shaded, but this one was not going to be shaded because undefined is not equal to 0. So we always not shade the points that actually produce undefined. But because we don't have equality here included, so we don't shade both. Then what do? We pick a value here which is negative. Negative, because a value that is less than a 0 is supposed to be negative. I'm gonna pick negative 1, and then I take this negative 1, I plug it here. Negative 1 times negative, I end up getting a positive, and then negative 1 times 2 is negative 2 minus 1 is still a negative answer. So I have a negative here. So a positive divided by a negative is a negative. So here I end up having a negative sign, and then I pick a value in between here. 1 over 2, the value that is less than is supposed to be 1 over 4, or a 0,25. I plug it in that original equation. If I plug in 1 over 4, which is positive, and multiply by negative, I will end up having a negative answer. And then if I'm plugging in here 1 over 4, I will get 1 over a 2. 1 over 4 times 2 is going to be 1 over 2 minus 1 is going to be minus 1 over 2. So I'll get a minus answer. Minus divided by minus is going to be a positive. So here I am going to have a positive answer. And then somewhere here I'm going to pick a value that is bigger, like 10 for instance, or 1 or 2. I'm picking 10 because it's guaranteed to be bigger than 1 over 2. If I'm plugging in here 10, I'll get a negative. If I'm plugging in a 10 here, I will get a positive. So I will end up having negative divided by positive, and then it's going to be negative divided by positive. It's going to be a negative. Now we have done with all the testing of the sign. Now when it comes to this, we are looking for the values that are positive. greater than 0, which are positive. So which means we are looking for this region which is positive. So the domain of the inverse is going to be x is an element of real numbers such that 0 is less than x and x is less than 1 over 2. And if you replace this with RF, we're always gonna get y is an element of real numbers such that 0 is less than y and y is less than 1 over 2. And this one here is the range of the original function. So we already have the range of the original function. And then just as a last example, in case you actually have missed something, let's suppose now we have y and our y is equal to x plus a 2, and then you divide this by x minus a 3. How do you deal with this, finding the range? First of all, we want to find the inverse. You interchange x and y. So when I see a y, I have to see an x there. Whenever I see an x, I need to see a y. And then here, we're going to have y minus a 3. And then here, because I want y to be the subject of the formula, I cross multiply. I am going to say that I'm having an x times y minus 3, and then this side I want to actually have y plus a 2 times 1, which is 1 and the same thing. And then when you're actually proceeding with this, you find out actually that we have xy minus 3x, and then I leave this as it is. Then since I have this nice thing this side, I want to bring everything to the left, so I have xy minus 3x. This is jumping the equal sign, is going to change its sign. Minus 2 is equal to 0. And then everything that have an y, I want to leave it on the left hand side, xy minus y. And then everything that have an x, I want it to take to the other side, and when it's jumping the equal sign, it's going to change its sign, so you're going to have 3x plus a 2, something of that kind. And then now that we have this nice function here, you can see that I can take y, and then if I take a y, because the common factor, I'll be left with x here. If I take this y, I'll be left with minus 1, and then we have 3x plus a 2. And if you look carefully to this, you'll find out your y is going to be equal to 3x plus a 2 all over x minus a 1. And then now that you have this nice curve here, you can see that the inverse of the original function is just 3x plus 2 all over x minus 1, and the domain of the inverse is just gonna be equal to x is an element of real numbers such that x is equal to 1. If you look, when x is equal to 1, this is the only case whereby this is going to be undefined. That's why we don't want that to happen. So we have this domain here. How do you find a domain? You ask yourself a question of what are the values of x that will make this function undefined, and then once you get those values, you just say you don't want those values, you cancel them out. And then if, let's say, you're getting something greater than or equal to, let's say you get something greater than or equal to, and then you say you don't want that, the opposite of that is going to be less than. And if you have less than or equal to is what will make this equation undefined. When you say you don't want that, that's supposed to be greater. And then whenever you have something less, and you say if it's less than this value, this is going to cause us a problem. You say you don't want that, the opposite will be greater than or equal. And if you have greater, when you say you don't want that, you're supposed to end up having with less than or equal. That's how you end up dealing with this. If you have equality and you don't want that, that's just not equal. That's what is important about this. And of course, we are not interested in the domain of the inverse. We are interested in the range that we get by replacing this by some f, which is equal to, replace this by y is an element of real numbers such that y is not equal to 1. So that is actually the range of this function using the inverse. Now the second method is, others they are saying, is finding the range of a function, but we're finding this range of this function by inspection. Usually when we are saying inspection, we are assuming that you can look into it and get what you are looking for, but in reality we are actually talking about composition of functions, or composite functions. So we will find this range using the idea of composite functions. Now, how do we actually use this function? First thing here, you have to spot the function sitting inside another function. So want to look for a function that is sitting another function and let it be g of x, right? And then the second thing is replace g of x to get a new possible a basic function and call it h of x. So we look for the function that is sitting inside another function, and then we replace that function by x, right? And then we also say now the new function is h of x. So we end up having two functions here, g of x and h of x. Now, what will happen here is this. This will happen, the original function, f of x is going to be equal to h of g of x. That's the original function, which is actually the composite of h and g of x. So that's what is important. Then, what do we do here? We say find the range. So most of the time when we are saying find the range, we actually saying that first draw the graph of the inside function g of x and find its range. So we are looking for the range of the inside function. Then we draw the outside function h of x and find its domain. So here we are looking for r of g, here we are looking for d of h, right? The next step is very simple here. The next step is saying that draw the number line of r of g and d of h. Finally, use the region where both RG and DH overlap. Use the region where both RG and DH overlap as the domain of h of x. So once we get r of g and d of h, we just draw a number line with both of them. Where these two intersect, we take it as a domain of h of x and erase everything that is not part of the domain. Then the new graph will have the range that we are looking for. It will have the desired range. Let's take an example here. We're just going to take two examples and then we can close, because this one is not one of the hardest things there is. Suppose the question is saying that find the range of y. Let me not use y for instance here. Let me just say f of x is equal to ln of I'm gonna look at cosine of x. Right, now that we have this, you can see that I have a ln function. Let me rewrite again here with a red that whenever we mean ln, we mean log e of cosine of x. Right, we know the function. Let me use this one here. We know the function y is equal to log base e of x, how it looks like. But here now we have this cosine that is sitting inside. That function that is sitting inside is the one we call it g of x. So we say g of x is the one function that is sitting inside, which is cosine of x. And then we say that if I replace this by x, I will end up having my h of x, which is equal to log e of x. Now, the next step is very simple, not hard. We just draw these two curves. Just draw these two curves separately. You don't combine them. Right. So we draw these two curves. So we have this, we have that, we have this, we have this, we have that, we have this, we have that, and then we have this, and then we have that. Now, if you look into this, you will end up seeing that here we have y, here we have x, here we have y, here we have x. I want to draw g of x. We know that if this is 1, cosine of x is going like this, and then it comes down, and then it goes up, something like that, and then this side also it comes like this, and then it goes like that. This one is not that good looking, it's wrong. So it's supposed to go all the way down up to -1, and then it goes up, and then it goes up to 1. So if you look into this curve, this position here is the one that is -1, and then this position here is the one that we call it a 1. Okay, this one is cosine of x. What is the range of this function? So the range of this function, everyone can see that it is an element of real numbers such that y is an element of real numbers such that -1, which is this value here, is less than or equal to y, and y is less than or equal to a1. That's what we have here. And then if I were to plot log e of x, log e of x goes this way, and then it passes through 1 there. And then when you have this nice thing here, you can see that the domain of h is just going to take all the positive values. So you're going to end up having x is an element of real numbers such that x is greater than 0. So this is the domain of this function. Now, you draw a number line. This number line here, I'm going to take these critical values. I have a -1 here. I have a -1, and then I have a 1 here. And then I plot some holes there. Equality means these are shaded. So these are shaded. they are shaded. So if you look at this, any value that is in between is always taken like that. That's what this thing means. And then looking into this, x is greater than 0. So the critical value here, I want to use a red. A red is always 0 is between -1 and 1. And then on top of it, I'm going to place a hole. This one here, the equality is not included, so we don't shade this. And then secondly, it takes all the values from this position and then it keeps going forever. Now, if you look at this part, these two, this range and that domain, they don't overlap, so you don't want that part. And if you look at this part, these two, they don't overlap, so we don't want that part. We are only looking for this part here. So this part is saying that we are looking for any value 0 that is less than x and less than or equal to 1. So you go back to this curve and look where 0 is. 0 is here and then 1 is there. Then we want all the values that are in between 0 and 1. So if this is going to be the domain, and everything else here which is above 1, we don't want that. Right. So we have a new curve. I can just say I don't want this part. I can erase it because the new domain that we have, 0 is less than x and less than or equal to 1. So this is the region that we're looking for. Now, looking into this, you will find out that the range of this function or the range of f is just y is an element of real numbers such that y is less than or equal to 0, because this one is included, it was included here. So we're looking for all the values of y that are below the axis. That's what this curve is saying. So this is the range we're looking for in this particular example. Now let's take one last example and then we can call it a day. So this one here, this is number, I'm not sure whether it's example 2, let me call it. We have example 2 here. Example 2 is saying find the range of, I'm gonna say f of x is equal to ln of the absolute value of x plus some pi there. Right, so this is a pi, and of course, like I said, whenever I see a ln, you must know that you have a log e of the absolute value of x plus some pi. Now, the function that is sitting inside the function that we know of, we just say is going to be g is equal to the absolute value of x plus pi. And then the remaining function after replacing this will be our h of x, and h of x is going to be log e of x. Now, if you look into this, the next step is very obvious because I want you to plot these curves, both the two curves, right? I want you to plot both the two curves, this one, and I also want you to plot that one. So this is going to be the curve like this. This is going to be the curve like this. Okay, now that we have let's say we have this, how does this curve looks like? We have been doing this curve like forever. The logarithmic function whereby this base is bigger than 1 is always looks like that, and that point is a 1, and then it goes like this, never touch the y-axis. This is the function, we call it log e of x. Now, if I were to plot this function, you must understand first that absolute value of x is just equal to x if x is greater than or equal to 0. This means that in this particular case, I have y is equal to x. In other words, as long as x is bigger than 0, I will have that. And I have minus x if x is less than 0. That's the meaning of the absolute value. So this curve is supposed to look something like this if x is greater than 0 or equal to 0, something of this nature, right? If I get this, then I will end up having y is equal to minus x if this one, if x is less than 0. So if x is less than 0, this side. Now, if I take a negative value and I multiply by a negative value, I will end up getting a positive value. So which means that this also will kind of look like this. It's going to look something like this. So that's how this absolute value of the modulus function looks like. But now I have plus a pi, which means we are shifting this a couple of pi units up. So this is supposed to look like this, and then it goes like that. And this point here is going to be pi. So I don't want this because this one was just telling me that I know the first part, and then now I'm shifting it up a couple of pi units up. These are x, this is y, this is x, this is y. Now, what is the range of this function? Of course, the range of g is just y is an element of real numbers such that y is greater than or equal to pi. Right. So that's the range here. The range is very simple, is y is equal to that. And the domain of this function is x must be greater than 0 because the log function is taking all the values that are this side. If you look carefully now with these two functions, you can draw your number line, the range and the domain. And this one have a critical value at pi. This one have a critical value at 0, and 0 is less than pi somewhere there. But let me take we're still at green, and this pi is shaded, so we want to shade this pi and want everything that is bigger than 0. So I want us to go this side. Now I'm gonna change this and plot this. So this one here is 0, and I place a hole on top. But this hole is not shaded because there is no equality. But I want everything that is greater than 0. So I am going this way. Yeah. This is too bad. So I am going this way. Right. Everything that is bigger than 0. But if you look into this, here there is no intersection. These two lines, they don't meet. You cut this part, you don't want it. And then if you look at this part starting here, they all overlap up until that portion here. So the domain that we'll be using now for this function will be, I'm looking for x, but I want this x to be greater than or equal to a pi. You come here and you look at pi. Is pi gonna be, remember that we're talking about x, pi bigger than 1 or less than 1? Pi is bigger than 1. You can always check it here, and then that's a pi, and you change it, it's 3 comma something. So pi is gonna be somewhere there. So this is going to be your pi. You go up to that function, and then you want to find out what is that value. Remember, this function here is log e of x, so this one here is supposed to be log base e of pi. This point here, you take the value of x and then you plug it there, you get that value. Right, now that we have this, of course someone else might say it's ln of pi, still one and the same thing. The domain that we're using is this domain, so anything that is not within this domain, we have to erase it. So let me come here. Anything that is below up until here, we don't want it. So we don't want that curve here. So the range that we're looking for is starting at this point and then it goes up. So the range that we're looking for of f is supposed to be y is an element of real numbers such that y is bigger than or equal to log e of pi. That's the range. Let me write it here. So the desired range of f is just saying y is an element of real numbers such that y is bigger than or equal to, because that point there is included, and then it takes all these values. In other words, we're going all the way up, is greater than or equal to log e of pi. And this, someone might say, greater than or equal to ln of pi is one and the same thing. So that's what is the range of this. I hope this actually explained some of the questions you might have when it comes to actually the range. So you can either use the inverse or you can use inspection. Whenever you start with the inverse and you get stuck, chances are you should try composite functions, or whenever you start with composite functions and you get stuck somewhere, chances are you should be starting with a different approach. But of course, not every time things becomes that pretty obvious. Of course, someone, when they're dealing with this problem, they might say that this is an inside function that is actually sitting inside, and they say I'm gonna let my y I'm gonna let my g of x to be equal to e to the power x. I'm talking about this, not this one. I'm just making a mistake here. Here they might think that, okay, this one must be just g of x, and of course I will end up having h of x is equal to x divided by 1 plus 2x, and then they try and plot this curve here. If it's easy for you to plot this, you can do that and follow composite functions, but for me, for this one, I just went straight to the inverse. So that's all there is when it comes to inverse and the range of a function. Thank you. Hope this lesson actually made a difference.